Chris Heckman. So Chris got his PhD degree from Cornell in 2012 in theoretical and applied mechanics. Did a couple of postdocs, winds up on our door. We hired him in 2016 in the area of robotics, where since then he's worked on perception and alignment of sensors, and then broadly in the area of field robotics. You may have seen him in the newspapers counting that sweet, sweet cash from Team Marble's third place win.
All right. Hey Chris, can I give you one tip? What? Up to the Zoom control bar on the far right dots. Those one? No, this one. Yep. Into high floating.
High float. Well, thank you very much.
Yeah.
That is, there are a lot of programs that go All right, so let's get started. So people settle in, they're cookies, thank goodness they're here. Wonder what I'm doing here. I want to share some footage from a recent project, DARPA Subterranean challenge, which Dirk just mentioned. The goal of the challenge was to develop robotic teams that could explore natural and built environments like underground tunnels, caves, mines, in order to find objects of interest called artifacts and build maps of environment. Implicitly, this is a multi-robot exploration mission with human-robot interaction with supplementary components. The challenge started in 2018, and when we were selected for funding as a part of the competition. And so we had about a year to go from having no coordination between all these PIs and all the students that were part of it, to having a fully staffed $1.5 million a year team that would be able to field a team of robots. And a few PhD students were interested, and we had a core that sort of stuck with us for most of the project. So there were 3 competition deployments. The first was in limestone mine outside of Pittsburgh, which was after 1 year of being on the project. The second was an abandoned nuclear power plant south of Olympia, Washington, and the final event was in an underground constructed course underneath the Louisville Zoo in what facility known as the Louisville Mega Cabin. All right, so the finals course was very challenging. The scale of the course was quite enormous. The large caves augmented with some constructed components that DARPA built over the course of a year, narrow caverns with challenging terrain, and elements thrown about by DARPA. So this is sort of an idea of the different scales and different kinds of environments that DARPA created for us. And to live up to their name and the tagline of DARPA Hard, the competition included a fully constructed subway ticketing station platform and tunnel about 100 meters in length inside of it. The single human supervisor wearing an orange helmet is pictured here was the only individual on the team to interact with the robot once they were past the starting gate right there. The interface of the system and how the supervisor would interact with that system with the robot is entirely up to us. We designed that ourselves, and that interface, how it looked and everything else was by our design. It's pictured here. And we had about 15 minutes to set up the system when we arrived on the course, simulating what was supposed to be like a real-life disaster response. So here I show some photos of the final event to give you a tableau of what that looked like. Consisted of constant testing, team meetings, discussions with other teams. It's really fun to be in a place where a bunch of roboticists, top notch, were collected and building their own teams and discussing the solutions. In the end, at the conclusion of the competition, our team finished 3rd place globally and 1st place among American-led teams, eking out a win over teams led by JPL and Harvey Nunn. But we had teams led by Norwegian Tech and ETH Zurich, as well as Australian PSIRO, which are both very well-known robotics groups across the world. We were able to. Oh, you want to move here? All right, great. Yes. Yeah, I know. Okay, is this better? Pick this up.
Much better, much better. Thank you.
Yeah, no problem. It's bolted to the table in case somebody wants to take that home. So we're able to walk through the course afterwards and observe the artifacts that we missed, and the enormity of the structure that DARPA had built up. It was pretty remarkable. It took them apparently a year to build the whole course. And in the end, like I mentioned, 3rd place got us about $500,000. And here was us after the team led by NTNU and ETHC as well as CSIRO. Great, so what am I going to talk about today? Well, I'm going to go into a little bit more detail about the DARPA Subterranean challenge and what our solution was at the challenge. want to talk about platforms and autonomy, those algorithms that we built in order to make the robots do as much as they could autonomously, lessons learned. I want to do a deep dive into some radar-based perception, and then I want to talk about my future directions and our research group's future directions. So let's jump right in. This is the Marble team. Those of us, I mean, the team is actually a really large team. I counted in the end, it was about 45 individuals. This is just the number of people who were participating with us in the final year of the challenge. And as you can see, we split the team up into basically sub-teams. One of them the platform team, another one autonomy, the communications team, and then there was the lowly managers at the bottom. My research group is highlighted in red here, the individuals that were part of my team. So there was also in the project management side, we also had 2 graduate students who were designated as project engineers, Harel Biggie and Jean Rush, as well as us, the PIs at the very end. I'll focus on platforms and autonomy for the next few minutes, to outline our setbacks and solutions, lessons learned. Unfortunately, I won't have time to go into a common solution today, but if you're going to IROP, I encourage you to seek out Steve and Harel. They'll be able to tell you everything they want, or if you just see them in the halls. So let's jump into platforms. Our hardware saw probably the most thrashing and changing throughout the competition. I'll try to paint a picture as to why. So we started with platforms. My group had on hand. That's what you do. Your experimental robotics group. You say, I'm going to go ahead and field a robot team. What do we have in the lab? Let's build a bunch of compute and sensors on top of them, and then new types of algorithms are going to be overlaid on top of that. And probably many of you had seen these platforms some years ago. The first one's the ClearPath Husky, and the second is a augmented, sort of personalized 1/8 scale car. In this case, we actually augmented this even further with some large wheels to handle some terrain. So talking about the parkour car, we had idealized this robot to be able to basically be a mobile comms platform. So that is that it would drive into the course and then be able to relay communications from between these different Huskies and human supervisor. What you'll also see is that it has a 2D LiDAR right here, as well as a radar. It had a very minimal compute stack. And that was basically that. On the left was the ClearPath Husky. There were actually 3 of these robots. We developed them with a sequence of gumball machine mechanism type dispensers for comms beacons that they would lay throughout the course and extend a comms network. It was instead outfitted with a 3D LiDAR automotive grade and 4 Intel real sensors for depth perception as well as visual. And remember, the point of the competition was to be able to look at where there are artifacts in this course. So what I didn't picture here, the drip fielding designed to keep the Husky dry. Just when you thought that Pittsburgh weather was bad enough, it actually rains in caves there. Yeah, they gave us $4.5 million for the course of the 3 years, and there was no limit for platforms.
Okay, you can.
Yeah, and in fact, many teams did. So our team basically operated only on what our group had on hand and the $4.5 million that they gave us, plus including graduate students in that calculation, staff, and everything else. Many other teams, in fact, augmented that with their own IRAD, so they were able to put whatever platforms together and support their team with outside research. It was kind of crazy to see the kind of competition that we were up against. All right, so the challenges that we saw. I just want to mention that this is maybe not obvious to you if you don't do robotics, but these are 2 very, very different platforms, even though they're wheeled. On the right-hand side, we have an Heckman steering type vehicle. This is very much like a car that you would drive. On the left side, we have a skid steer vehicle, which means that it can actually turn in place. And so this means that you actually need 2 different planners. We didn't really think about that when we were going into the competition. And furthermore, we didn't think about how narrow the tunnels were going to be. The tunnels were so narrow that this thing would actually have to make like an 8-point turn to be able to turn around, versus this vehicle, which could actually just stop, turn around, and then go backwards, right? So this was a really remarkable change. And for us, we didn't identify that until very late in the game. And so a single false move would be catastrophic in tunnel, because if this thing got stuck against the wall, this one might not be able to pass by it because the tunnels are so narrow. So there was actually a couple of lessons that we had to even learn from this, which was that we needed reliability before speed. We thought this thing would be moving very fast, and reliability is very hard, which means that you never actually get to speed. Okay, so in fact, like all of the platforms throughout the entire competition never moved what I would consider fast. Like a light jogging or fast walk pace. They were more walking at like I would say a delicate walk, like stroll in the park, as they were trying to like find survivors in an emergency response scenario. So, I mean, I think there's some things that I want to talk about with respect to that as we go forward. Okay, so that was up to tunnel, and then we thought to ourselves, our team is like, okay, we need to change things a little bit. We're going to ditch the fixed multi-real sense camera configuration. There's a couple of technical reasons behind that, most notably that a lot of USB cameras hooked up to the same computer tends to cause bandwidth issues on the USB bus. So we just decided to go with one USB camera. And then we also, as you can see, did anything related to Heckman steering. So we had two different types of platforms here, really. One of them was this Husky, and then the others were these tracked vehicles. The tracked vehicles we were hoping would act a little bit more like the Husky. They could turn in place, but then they would also be able to go upstairs if you were able to align them right, and then go over sort of tougher terrain that might be a little bit sandy or something else. So this is the idea that we would extend our solution by adding these track vehicles. We also added a quad rotor into the mix. And we actually did very well with developing a quad rotor in only a course of about 6 months. Competition for tunnel was in August. The competition for tunnel or for urban was in February. So this was basically what we had, thought as being a simplification, in fact, of our solution. Does this look like a simplification to anybody? Yeah, no, it's not. In fact, this is a disaster, okay, for our team. And I just want to be very blunt about it, because I think that we sort of lulled ourselves into thinking that you're changing things and making them easier, but in fact, we actually made them enormously harder. Track vehicles require completely different terrain classification systems than our Husky. It would high center all the time, would honestly just go maybe 20 meters before it found something that it could high center on, and then it would basically go right for it. It was remarkable to see the kind of bad behavior we saw from our planner. And we didn't actually think about how that terrain classification system would need to be re-engineered for these track vehicles. So that was a huge mistake. The UAV worked very well, but it needed about twice as long as we gave it to be able to deploy it enough times and test it to be part of our complement. So we actually ended up not even flying in any of the missions for urban, even though one could argue that it was ready to go. And the last thing to note is that what was our performance at urban? So at urban, this is those on the team know about what I'm going to say. We tied with 3 self-funded teams, the ones that didn't get a dime from DARPA, and we actually placed last among all the funded teams. And so we actually thought, okay, this is an absolute low point for our morale. Like we need to completely reconfigure, and let's have a bunch of meetings when we get back home, figure out what went wrong, and then all of you know what happened February 2020. Okay, so COVID, 1 month later, we can't even meet. We can't even work on the platform anymore. So this was a real shock to us. We had to make a crazy number of pivots in terms of staffing, platforms, algorithms, and even just like morale. How are we going to stick together through this event? So we took a step back and we reconfigured. So my conclusion here is it's hard to tell when we're simplifying something. That might be obvious to some of you, but I think that's it's important nevertheless. So COVID was a reset to us. The team decided to have 2 graduate students take on management responsibilities, Harel and Jean, as I mentioned previously. I attribute our win at finals to them. They probably worked between 68 and 80-hour weeks for about a year. Maybe they took some vacations because we told them, please take a vacation. They took their responsibility very seriously. And what I also recognized was just principal investigators. We have multiple other projects. DARPA was not it. I was teaching at the time and had 5 other projects. You can't just drop all those things and do sub-T, right? So project engineers, people who are in the trenches with the scientists and engineers working on robotic platforms, that was really a necessary component. Our final loadout at finals was this. The Husky, the compute stack is largely unchanged. You'll see that we did streamline a few things and we significantly simplified our beacon deployment system. We actually decided to go with the same perception head, as I'll call it, between the Husky and the Spot. So there was very little re-engineering that was required across platforms. We decided to downscale to only 6 beacons that could be deployed from the back of the Husky compared to those large number of beacons that was shown with the gumball mechanism. And in the end, the Spots actually were really a game changer for us. The reason why was because they actually had their own terrain sensing capabilities, so we didn't have to re-engineer a terrain classifier for them. That is the idea of where it could walk and where it would get stuck. And it actually had a very similar compute stack and sensor platform, like I mentioned previously, to the Huskies, which means that we could work with a combined sort of similar platform between the two systems, which was a huge time savings. The spot allowed us to traverse more tortuous terrain, allowed us to go up and down stairs without engineering anything much at all. And finally, it walked about twice as fast as our Huskies drove. And so that means that it actually did get speed without even having to do any special engineering associated with it. It was pretty remarkable. We also developed a UAV stack that could work, but it could only go out from the gate. A lot of other teams, they decided to build out what are called marsupial solutions, where a UAV would be sticking on the back of this thing, UAV would drive in, and then the vehicle would drive in, and the UAV would launch. There were a couple of software decisions that we had made very early on, like 2 years before, that nearly made that impossible for us. Like, how do you turn on a robot and then tell it where it's been? Like, even that state serialization problem was not something we had engineered at all. And to be able to re-engineer that into our stack would have required changes to the foundation of how our system was built. So the two lessons here, some features are conditioned on very deep and early design choices. You don't even know them until maybe years later. It's very hard to see these when you're making those design decisions that are supposed to be simplifying, right? So I think that that's one observation. It's actually very difficult when it comes to these robotic systems to backthread. The second is that terrain traversability remains a keystone capability. We had devised a pretty good terrain classifier, which I'll go into some detail on in a second, for the Huskies. The spots, we got it for free, because these spots told you basically with their cameras, you can drive over that, I can't drive over that. If you make me drive over that, I'm going to bounce backward and I'll actually walk around. That's the benefit of a purchased platform. So I just really think that those two are two really important points to make. Speaking of sensors, here's our perception head viewed sort of as close as possible. We have a 64 beam automotive grade LiDAR, essentially a high accuracy IMU here. We were able to do extra terrain classification using flash LiDAR systems, and we had replaced the USB cameras with gigabit Ethernet cameras. And I think this is pretty funny. At Urban, one of my friends, Matt Hudson, who was a PI for CSIRO, the one that placed second, also a colleague of mine right now at Amazon, gave me some really great advice on how to solve the unreliability issues of USB cameras. He said, don't use USB vision. All right, so let's talk about autonomy solutions. So we developed what I would call a pretty lean strategy. And this was something that I think is a template that you might be able to see in commercial robotics applications, or at least that I've seen in my experience in commercial robotics applications, which was that we had this home-based solution, which was reliant on vision. As you may recall, a few years back, I gave you a talk on how we were building machine vision solutions for state estimation and robotics. And so that was developed by one of my PhD students, Brandon Obrey, into a package called Compass. We had modified that and added in some inertial measurement units integrations into that so that we could work supposedly in this low light environment. But what we had identified is that these kind of vision-based systems, they don't work very well in low light. There's a lot of motion blur, and bringing the light along with you actually sometimes breaks the front end of those vision systems. So we decided to adopt something that I had never done before, which was put a LiDAR on the robot, okay? Just like what everyone pretty much except Elon Musk decides to do with automated vehicles. All right, so we put a 3D LiDAR, and in order to avoid these tracking failures as a result of specular highlights and future force scenes. We also decided to go with a off-the-shelf open source solution called Cartographer, and we iterated on Cartographer through the course of the competition. So we decided to go and get an open source solution and modify it. And as the competition went forward, we went from 2D Cartographer to 3D Cartographer. We sort of broke off a little tighter team of engineers to be able to look at other types of LiDAR inertial solutions. In the end, we went to something that was hot off the press, not even developed by the time the first competition rolled around, which was called LeoSam, an open source package for fast loop closures and LiDAR inertial odometry and smoothing and mapping. This was all open source. There's a few modifications in our system. And I think that it's important to note probably two things here. I'll just note one. One, if you're bringing the light along, because it's a dark cave, then it might as well tell you exactly how far you are down to centimeters away from walls, right? I mean, that's pretty nice. The second thing is that I think that there's a vast underappreciation for well-engineered software solutions at the academic level. This team right here is an academic team. They created this LeoSAM package. Now LeoSAM is being used by there are companies that use it. I mean, our team used it, other teams evaluated it. So I think that it was all because you could actually download and use this package. And what was this package built on? The hard math of LeoSAM is actually built on another package called GTSAM. And GTSAM is a optimization backend library that's developed by Georgia Tech. So academia actually has a lot to give in terms of well-engineered solutions. This is a pretty big difference from what we usually see in terms of, you know, oh, I get to the paper level and then I release my code and it's just sort of like, here's my GitHub repo, right? I think that there is actually a lot of work that can be gleaned from an extra emphasis on developing a robust solution. All right, the next addition, what we did in the competition that I want to talk about is this terrain classification. Like I've talked about it a lot, and I want to talk to you about how we solved the problem. So prior to the cave circuit, so basically at Urban, we had only had maps that constructed what are called obstacles, which are like things like walls, you know, maybe something large structures related. This is the idea that if something's sticking out of the ground, you can't drive over it. But there was nothing contextualized about the map information that we were collecting and generating based on sensor data. So what did we do? I mean, I should say the result of this was that we had no idea whether something was actually drivable or not. We just kind of came up with some ad hoc control systems that would either avoid or drive over something based on how tall an object was, essentially. We needed to be able to map traversability. So one of my students decided to augment our mapping system with the classification of geometric measurements that were fused into the occupancy map that were only working on two quantities. One of them was the direction of normals, and the other one, the normals to a surface, so normal vectors. And the other was how quickly the direction of those normals change using a 3D convolutional kernel that's mapped over this terrain. The idea then is that if you have these normals that are changing really rapidly in a small spatial scale, that might be something that you can't drive over, like these two rails here. And what we're going to do is we're just going to light those up a little bit. We're going to flip a bit on them. It's going to, not just a bit, it's a scalar value that essentially says, maybe don't drive over this thing, right? This is pretty innocuous compared to these walls, but it's definitely something that we can tell is high frequency, spatial frequency in terms of normal changes. So we just embedded that into map information. We found that actually to be very robust for safe navigation. We augmented that. We found that that worked pretty well. So we augmented that with a few more kind of contextualized pieces of information that we would share in maps between different robots. So we labeled traversability. We also decided to label stair presence, and we decided we could also add a few more things in if we really wanted to, like whether we think that there's maybe an artifact here and the human supervisor should look at it, even if maybe the cameras didn't pick anything up. So this was compatible with our existing differential-based map solution where we change deltas between different robots, and we consumed this by a planner that would also be able to say, okay, not only do I have a low-level control system that's trying to avoid something that is maybe non-traversable, but I also have a planner that's going to avoid it. So this was all put into this one system where we had terrain classification, stairs classifier, all going into a mapping system that was then exported through a mesh comm network with map sharing, and the planner would operate directly on this Optimap with a labeled merged map from different robots. That was the idea. The note that I want to make here is that map data with contextual encodings can provide us a lot of extra information. This context of maps is very important. And I think that there's actually a lot of research to be done that has not been explored in this area. That is to say, what we like to exchange maps that might look very pleasing, something that's like a 3D geometry, maybe with some RGB information attached to it. And our brains can look at those RGB occupancy grid type maps and say, oh, maybe this is bad for the robot and this is okay. We can decide to augment this with a bunch of other information that is just like dense feature vectors that are potentially trained over what is traversable and not traversable. That's one of the future research directions for us. Yeah.
Technical question.
Yeah.
If you had something very bumpy.
Yeah.
If it was like, I don't know how to say this right, but I could imagine something like a mat with a whole bunch of bumps on it that you could drive over, but still the frequency of normal.
Yeah. So this is a great question. And actually it's the point of research that's coming out of like the deep reinforcement learning folks, because using something like what we did, we already are, you're right, conditioning ourselves on that we kind of have an idea of what is traversable and not traversable. What is DARPA going to throw at us? But it would fail on grass, right? Grass is obviously something that any one of our platforms would be able to walk over, but our terrain classification system would say, no, that's not great to walk on or drive through. And so how are you able to include information like that? Well, I mean, obviously our classifier is bad, but you can create even more like data-driven classifiers that would be able to say, in fact, I have driven over grass before and everything's fine, right? I think that's an important aspect. If you look at grass from a 3D geometry perspective, it looks like, you know, one of those pits that you fall into, a pitfall, you know, like a very spiky, you know, it's very bad, right? But if you know that it's flexible or compliant matter, then you can go ahead and drive over it. I think that's an important aspect. Great. All right, so I want to talk about the mission management. Like the human supervisor's role is something about human robot interaction that I talked about previously. The mission was managed by a single human supervisor. I think we really lucked out to have an active Air Force colonel on our team, Dan Riley, who was actually our human supervisor, worked out really well. Dan earned his PhD with Air Crew last year, was our sole human supervisor the entire time, and took charge of tasks managing artifact reporting at DARPA, even some deconfliction between robots and paths, being able to, in fact, at times directly tele out the robots with a gamepad. You'll see here the orange areas in the status of these bars. Those are places where he actually had to take over the robot. And you'll see one happen extremely early in the competition, go through this narrow cave when we had a risk tolerance for something that's a little bit not that narrow, right? We would have actually missed out on a pretty large portion of the map. And so there were actually some places where we scored quite a few points as a result of his taking over in those systems. And here's just one example of where those places were. Here's this narrow cave, and without going through this narrow cave right here, all of these portions of the map would have been completely unexplored, would have never been able to get there. So there were places where actually human supervisors interaction is really necessary. For those of you that are interested in these sorts of statistics, our percentage in green was about 52%, which is really, really good for a 4-robot system, like remarkably good. I think that's, you know, per each robot that ends up with something like 80 or 90% percentage in green, where the system is operating autonomously without any interaction from a human. And the whole system mean time in green, that is the ability for us to autonomously operate, was 3.5 minutes, which if you were to scale out to each robot, is about 10 minutes per robot of mean time in green, 10 minutes before you need any interaction from a human supervisor. These are actually really good teleop numbers. And pretty much every system today, autonomous robot system, has some sort of teleop behind the, you know, it's sort of a Wizard of Oz waiting to step up. Yeah, what's up, Jerome?
So did the human actually decide when they were going to take over, or was there support for that?
Yeah, so the human decided when to take over. There was no way that we could tell, oh, this human shouldn't take over right now, or I need the human's help or something like that. The other thing is that no artifact report was made without a human's fingerprint on it. We had a limited number of artifact reports, so that means a human had to actually greenlight the artifact report in some way. I think there's a lot of research to be done there too. So I want to talk about some key takeaways. And I call this, are you anyone interested in founding a startup slide, which is because if you are, then I'm going to try to give, I think, some hopeful advice, maybe. Take it or leave it, whatever, it's up to you. Here you go. So first of all, there's a very delicate balance between validating and practicing and developing. And this is, okay, so at first glance you say, yeah, I know that. Like, you know, testing, practicing takes time, developing takes time. So clearly there's a balance. There's another balance that I want to tell you about, which I found to be very surprising. Towards the end on our team, I found, or at least I came up with this observation that our team looked much more like a NASA-like mission, launching something, than like a scrappy, innovative project. And by that, I mean, like, everything that was tested was like flight ready. Everything that was untested was not flight ready. If it was flight ready, it went. If it was not flight ready, it didn't. It didn't go, right? So that means every kilometer that we tested something was a cost that we would have to re-incur if we decided to change that component. That is what I'm talking about, right? So this is like a less than obvious point. that if you decide to drive 100 kilometers on one component, then you say, let's throw that component out, put the one in, then you have to actually drive 100 more kilometers on that one to be able to answer whether or not this one is better or that one. Very hard to do that, right? So that's a cost. And the last thing I'll note is that the final 1% of errors in our system were like what I think were Poisson distributed, which is like to say they could happen at any moment and end the mission. And it was hard to evaluate what the statistics were on that event occurring, which means that essentially, if you came up with a solution to one thing, then you wanted to stick with that one, and you didn't know whether or not changing something somewhere else would incur some other new Poisson type of distributed error that you didn't get to see until maybe hours into testing. The last thing, or the second thing I'll note is this idea of outsourcing and buy versus build. I'm sure many of you are familiar with the notion of buy versus build. So partners that brought in technology, like Boston Dynamics, another company named Meshmerize, these were very good. We were able to buy their technology and then be able to just work it into our system. If we had to build something ourselves, we found at times there was an option of like, do you want a contractor to do this? Or maybe some sort of consultant. And this was very expensive, and we never even owned the idea afterwards, which means that we always built it, right? So and nevertheless, this is a very hard balance to strike. I find that like if you can buy a platform, that saves you a lot of time. That's the last thing I'll note about that one. I think that the foundation for autonomy is still missing when it comes to these sorts of missions. The industry is still seeking what autonomous platforms look like. There are some possible options like people and companies that are interested in building out like OSs for cars. Phantom Auto, I've heard is one of them, but that foundation is still missing. So if you think that you can build on an autonomy foundation, that is already a mistaken idea. Like there is no autonomy foundation for operating in the wild. So I think that there's still work to be done here. The last thing is that, and this is one that I've seen even in teaching classes, but definitely on this team, personnel and project management is vastly understated. So we have an idea, I think, that TPMs or technical product managers or program managers and managers, like actual managers of applied scientists or engineers, they help mitigate this sort of management problem. And I would say that that's partially true, but also partially false, in that those managers and TPMs can sometimes end up a little bit out of the loop, not for any fault of anybody, but just that engineering conversations happen very rapidly and in ways that are just like, oh, let's two people talking while they're at the computers, right? And so if that manager isn't there, which they're generally not because they have a bunch of meetings and other things to manage, then these decisions may not be actually well communicated across the team, even if they have large implications. Those engineers may not be aware of all the implications they have. So prioritization among small teams of engineers is actually very important. They need to be like a team of a bunch of equals. The decisions are being made in a corporate way. And so that's why we ended up finding that project engineers are those individuals who are full-time doing technical work. We're actually sort of like very useful tiebreakers for those type of things and communicators. They would say, oh, this is actually something that this other person is working on, or this is a problem that we've actually observed on this test. So those are my thoughts. At the conclusion of the final event, there was a PI roundtable. Okay, so this is all the PIs, and they're sitting, there's the program manager. At this PI roundtable was very interesting. Many PIs asserted that there was parts of this problem, at least, that were so-called solved. Many areas were said to be solved that I think I took some exception to. And I want to take some footage here and explain to you why. I believe, yeah. So this is the top scoring team, Cerberus, team that was led by NTNU ETHC. And this robot stands here at the final event for 2 minutes doing nothing, right? Okay, so what is it doing? Maybe planning, might be waiting for human input. It's definitely not acting in like what I would consider to be an urgent way, right? Be out to lunch, right? Okay, I could go on for 2 minutes, but I'm not gonna waste your time. Here's the CSIRO team. And has anyone seen this footage, not sub-T? No. Oh, yeah. So I don't think environmental disturbances are well solved. Yeah, all you graduate students being like, oh no, you can only imagine how much time is spent building that UAV. So that was the second place team, right? And I'm not going to just like, I'm not going to claim that other teams have all the problems. Here's a video from our robot. very casually standing around, getting a little bit flustered with the terrain. I mean, this is all like autonomous mode, like, and still in the same corridor. And yeah, that robot was out of commission, right? Totally done. So I just want to say, like there's still a lot I think that has to be solved. Terrain is one of them, coordination, moving fast. I've already touched on these issues. I think that these are issues for future research. And I want to say, like, here we are, we scored pretty well, 18, the top 2 teams scored 23. We were pretty far away from them, but these scores were out of 40. So like 23 out of 40 people were saved, right? 18 out of the 40 bombs were found. I don't know, I mean, like, this is not good, right? Like, we still have a long way to go. And yes, I would say that it's very surprising. We've learned a lot about what we can do with autonomous robots and teams underground in challenging environments like this one. But we still have a lot more work to get to where we're very confident about this. We're deciding, like, we're going to save human lives, not send them in, and send the robots in instead, right? I mean, okay, so those are my notes there. Okay, so now I want to deep dive. This is a bit of a gear switch, but it's motivated by exactly what happened at the Subterranean Challenge. In fact, the R in Marble was radar, which is what I get to talk about now. So I saw one unsolved problem from Sub 2, still unsolved at the beginning as it was at the end, which was being able to work through these kinds of what are known as visually degraded environments, or VDEs. And these visually degraded environments, like one example of them is when you have fog or smoke or something else, where usually light would be backscattered and diffracted across it. And what you end up getting if you're building a 3D map of this type of visual phenomenon is sort of these spectral beings sitting in your way. And what if there's this obstacle sitting in the way of this map? I can tell you what happens, the robot will turn around. Okay, doesn't know what this thing is, and it knows it can't get past it because it's there, right? So I think that that's something to be considered. Here's an example of a full stack of LiDAR inertial odometry with a front-facing camera. And you can see that if I fill the room with fog, then this entire map becomes filled up with all these voxels that are saying it's basically you can't get through it. The one thing that maybe wasn't obvious from that is that also the tracking on that camera was really bad because it was using visual tracking and it got confused by the fog. Environmental challenges aren't the only problem. When we're trying to solve problems in subcomputer vision, we observed that when we were carrying an onboard light source, the appearance of the scene is heavily dependent on the robot's pose or how it's positioned against the geometry. And this results in many undesirable effects, such as illumination drop off, like very bright sparks here, but nothing past that exposure, similar kind of effects. But in this case, it was essentially even worse, affecting the exposure times, auto exposure times of the camera. Motion blur, which is no surprise if you've ever done any video in dark areas, or specular highlighting, things that are shiny that end up being unresolvable. Okay, so these are just some of the problems that we identified. Of course, if landmarks and geometry can't be tracked, then odometry estimates also suffer. So we have no idea how we're moving in these environments, not to mention what the geometry is inside the environment. So this is actually a really hard problem to solve with vision, vision and anything vision related, including LiDAR. LiDAR operates very similar frequency spectrum as vision, has the exact same problems. Okay, hence my group set out to try to solve some of these problems with millimeter wave radar and look at what is this as a sensor. So we're new to this, but so is everybody else. Might be surprising. Radar's been around for decades, right? Nearly a century. But new development in sensor fabrication has resulted in very small radar sensors, such as this one pictured here. So this, if I want to show you, the banana for scale, like that's about the size of the radar sensor, and the bananas, this is pretty small, is the idea. It's like credit card size. Okay, so radar, as you know, provides detection and ranging information similar to LiDAR, but in the millimeter wave case, the frequency of the EM waves that are emitted from the sensor are about 4 orders of magnitude lower than that of vision or LiDAR. Meaning that we see refraction and backscattering on very different types of matter. Okay, so if you have a characteristic length scale about 4 times or 4 orders of magnitude longer, then you can actually go through fog, and you can go through a bunch of other things like water vapor, sometimes even light rain and snow. So that was one of the areas of interest that first spawned this. We can penetrate haze, dust much better than LiDAR and vision. So, okay, radar gives detection and ranging information. That sounds a lot like LiDAR. Sounds like we just use LiDAR methods, right? So here's a video of these red dots that are showing up. These are radar returns, and the green dots are LiDAR returns. First of all, you'll note that, of course, radar is much sparser than LiDAR. The second thing is that these radar points are just showing up very randomly and all throughout. They seem to be clustered around the green points. I know there's a 2D projection of 3D geometry, but bear with me. But they're just unreliable. They're showing up in different like spatiotemporal frequencies even, right? It's like, okay, they're kind of reflecting off of these points up here. We're all going to really like that car. It's made of metal, what do you know? And there's also just like stuff that's showing up in the middle of nowhere, or is it? Because you can kind of see some green points that are right next to the sensor. Other things that are very different is that they're very sparse. So you can see that these green bands, you know, there are maybe thousands, tens of thousands of points per scan. Radars typically have about 200 points per scan. Some of that has to do with signal processing limitations I'll go into in a second. And so in addition, there's very little repeatability from scan to scan, which is all that motion that you see here. Radar sensors also tend to provide or tend to produce a large number of positive or false positives, places where there isn't necessarily something. So how do we get past all this? This is the challenge associated with radar. And as many of you might imagine, just like how LiDAR and vision are moving, we have been vastly inspired by new methods in deep learning. So let's talk, before I get into algorithms, let's talk about some radar sensors. This is not the only radar sensor out there. If you look at the literature in robotic perception, you'll see two different types of radar sensors that are commonly used. The first one, and much more popular one, is this 360-degree 2D radar. So this is a scanning radar. It uses a pencil beam type of beam form, and it provides something that looks a little bit like a 2D LiDAR scan. They are heavy, they're power hungry. This one pictured here is 6 kilograms and uses 30 watts. And it doesn't really, you can't fit this thing on a UAV, and you probably wouldn't have even been able to fit it on top of the Husky in the Subterranean Challenge very well. So the radar that we're talking about, of course, is much smaller, 0.03 kilograms and 2 watts power draw. Uses the same frequency spectrum, but there are some idiosyncrasies for it. I want to talk a little bit about how radars work before I start going into some solutions that we've developed for them. So this is not like an RF engineering sequence of slides, so don't tune out if you're not familiar with radar. So our radar sensors return targets that are parameterized by range, azimuth, elevation, and Doppler. Doppler is, as you probably know, like approximately equal to or it gives some measurement on speed of an object or relative speed of how we're moving against static objects. So if we assume the sensor platform is moving and all of the objects in the scene are stationary, then the velocity of the objects in the scene relative to the sensor has equal magnitude in opposite direction to the velocity of the sensor platform, right? That's just, that's relativity. Something is moving or we are moving with respect to it. An object's Doppler measurement, however, is the projection of its relative velocity vector onto the ray between the sensor and the target, this thing right here. So you can see it is not the velocity measurement of the object. It's projected onto that ray. If we have Doppler measurements of many objects that are distributed throughout the scene, we can actually regress the velocity of the sensor platform. Not that obvious if you see it the first time, if you are told it, but you can see here that this is actually providing small measurements along these rays, that if there's a constellation of these targets, we can actually regress the velocity of the platform. So this is what we identified, and we started writing some papers associated with it. This provides us a direct observer on velocity, something you do not get from vision or from LiDAR. It's pretty remarkable. This is reflected in this Doppler sensor model, where the true radial velocity of the target is the dot product of the local frame velocity of the sensor and the unit ray between the sensor and its target. So it's possible to use this model alone to estimate the sensor platform in a local frame. That's pretty cool. But there's a large amount of noise in Doppler measurements, which make it pretty unreliable for estimates if you were to just do some sort of averaging or mean calculation. So we have to do some trimming and some signal processing. What we're going to do in order to do that is we're going to use an inertial measurement unit. Now, this actually should seem familiar for those of you that saw my reappointment talk several years ago. We've been using IMUs in vision for a long time. IMUs, if you're unfamiliar, they provide very short-term spatiotemporal constraints on motion. It's basically like the semicircular canals in your ears. They provide a very noisy measurement of it, though. You can't just rely only on an IMU for state measurements. You need to provide it with some other kind of information. So this is all put together in a factor graph wherein Doppler targets are connected to states, and there are inertial measurement unit factors that are basically these pre-integrated IMU factors between the different states in time in order to determine what the local frame velocity, attitude, and IMU biases are. We estimate these states by minimizing a cost function, which is shown here, which is sliding over the last few couple of measurements, so maybe K measurements that have been collected. And this is just a minimization. We're minimizing this error associated with the Doppler term that I showed in the previous slide, and some inertial term, which again provides us these short-term spatiotemporal constraints. All right. So we actually did refine that method a little bit in order to get to a place where we could do active state estimates, because to this point we've only been able to get velocity estimates. So the biggest change is that we often estimate those velocities in the global frame. So if we are looking at this in terms of what we just showed, all of this is the same, but now instead of doing some batch optimization of the previous measurements, we are also going to be doing a marginalization using a Schur complement method in linear algebra. This is a single marginalization error term, which you're familiar with, like visual inertial methods. So what this looks like here is this modified Doppler term, and the same inertial term is unaffected except for a body change of coordinates. So this was a sequence of papers that we wrote that actually ended up with very good results, and I'll show them in just a second. That was I'm sorry about that. This is this animation. I spoke past myself. So the error in radial velocity measurements and error in range measurements are just the previous terms that I showed. The velocity error here is going against the motion capture system. This is in time. And what we have here is that the meters per second error. And what you'll see is that the radar measurements, while noisy, actually do compare very well with LiDAR and visual. And this is in a non-visually degraded environment. So this is the best you can possibly get from vision or from LiDAR in X and Y components. So this is actually something we can close a loop around because we currently close a loop around it, which means what we've demonstrated is we can come up with a solution that actually we can close a loop around in visually degraded environments as well. So that's state estimation. I want to talk about mapping. So traditionally what we have is something like an occupancy grid mapper on the left. This is using a beam model wherein a LiDAR might cast some voxels and then hit an object, and then you have a probability of that there's an object at this certain location because the beam stopped in that location. Same goes for this. Everywhere else that the beam did not stop, continued, we have a decreased probability of there being some obstacle. That's not how radar works. Radar likes to go through things just because of that millimeter wave that I was just talking about. We came up with a new radar model for these types of occupancy grid maps to be able to identify where there are actually likely objects that may actually be behind other obstacles. So this was one modification that we made. It's actually worked out fairly well, as shown here. So what we have is these green dots and red dots are both radar returns, and this new mapping solution is picking up all these different geometries in the scene. So I do want to mention one thing though. This green and red dots, like you can see that some of them are still out in the middle of nowhere, and this map is pretty sparse. So what we have done is we actually took this kind of input and we supervised these red and green dots with these LiDAR points. And we threw them into a convolutional neural network, this is a convolutional neural network based on the PointNet architecture. In fact, this is PointNet++, and it uses the segmentation architecture. So what we did was we said, if you have a LiDAR point within some distance of a radar point in 3D space, I'm going to call that a false positive or a true positive, and everything else is a false positive in terms of my radar point. With this, I can actually learn where there are places that you might have a real return, a real geometry, and then places where you should be ignoring it. So this gets rid of that false positive fact that I was talking about before. So if we do that, then we can use these red dots are now outliers as determined by this neural network. The green dots are inliers, and this is one example of how we were able to do training on this neural network. So what does this learned outlier rejection look like? In this case, we're now running that same Octomap package with now the updated beam sensor model that I had shown, or radar sensor model that I had shown. And you can see that the points actually, because they can be tuned for false positives and false negatives differently, the maps end up far denser and only in places where there are LiDAR points. Now, all of a sudden, we've taken these really garbage radar points that are super noisy and getting multipath reflections everywhere, and able to build a map that we can operate in. So we've solved both problems of autonomy, the foundation of autonomy at least, state estimation in these kinds of environments, as well as 3D mapping in them, which means we can do planning and we can do control and everything else that we need to do for things like the subtlety challenge. But in this case, we ended up developing it for just this test grid, which I'll show. So here we have a pretty simple motion primitive type of planner. So it's giving us different directions that we can move and we can choose among them. And this is operating in the engineering hallway. We also show a heads-up display of what these points look like as they're projected in the camera view. And you can see here that most of these points are sort of sitting on these walls. And we also visualize the Doppler measurement to show that there is some noise or some signal in these points that are coming across. And here we're showing that, okay, you can actually, if we were using a planner, like the planner would say you can't drive or fly here, and you can fly in these green directions as a result of objects that are around. Now, this is all just like, a beginning of this project. There's actually many other places that we'd like to take it, including different radar applications or different data-driven techniques that are built on data sets. And the last thing that I'm going to talk about today is the data set that we created. So signal processing target detection algorithms used by automotive sensors are designed to answer single quantity queries like how far is this car ahead of me, right? So you send a radar beam out, it comes back, you get some range as a result of the time of flight or that phase difference in this case for millimeter wave. And what we would like is to be able to generate arbitrary data sets that people can do training on, like what we have in terms of vision and LiDAR, like this one example, the EuroC MAV data set's a very common one. There is some radar data, there are some radar data sets out there. One of them is called the Oxford Robot Car Radar data set, built by a team at Oxford, but it is using that automotive radar that I previously described. Thousands of kilometers of driving, it's actually a great data set. But our goal was to be able to do this with this imaging radar using millimeter wave on this automotive type of grid. And there's a lot of technicalities that were involved in this. So all those points that we had, that would make one great data set, but we wanted to do better than that. What we ended up doing was providing more dense information, which ended up having to essentially pack into this sensor and then try to extract the data that was before this sequence of filtering that resulted in those 200 points per scan. And so what we ended up getting was going to be demonstrated here in just a second, dense radar images, raw ADC values, analog to digital conversion values, and those points. So you have multiple entry points into looking at what these radar data look like. As you can see, these radar data are far denser than just those points. And I'm doing just a projection on a 2D. This is actually a 3D image. So it's a 3D intensity image that then we can try to learn where are there different pieces of geometry. You can even see from this heat map as shown here, written or run through our signal processing techniques, that there are some resemblances between the LiDAR and radar scans. So this is one example, walking through the engineering center. Another example is one of my former students, Andrew Kramer, taking his electric skateboard and driving down the Boulder Creek path. So this is an outdoor data set. And then we were also able to collect some data in a subterranean mine, former gold and silver mine called the Edgar mine in Idaho Springs. So this is just another example. So I know I'm near out of time. I'd love to take some questions. So I'm going to just talk about where we're going after this. So I think that, there are 3 projects that I cannot talk about today, obviously. Wish I could have, but one has to prioritize. Multimodal robotic perception is one of them. I've been working a lot with Martha and a number of other members of our NLP team to look at how we can build out different representations and multimodal representations of vision and language. I think this is a future direction that we absolutely need to pursue in order to get past some of these speed arguments associated with robotics today. Right now, for instance, for a human to be able to interact with a robotic team, they need to be able to go in and drop waypoints, and they need to work with the robotic interfaces as I had previously shown. There's a lot of bandwidth in language that we are not able to capture right now. Things like go to the end of that hallway, stop and wait for my next instruction. That would be an excellent interface that we cannot yet do, right? That situated understanding between 3D geometry as well as vision and language is just not something we have today. So that's one area that I'm really excited about. And I think it's going to be the future of robotic planning. We'll see. Check back in 6 or 7 years, but I think it will be. So verified control is another one of them. I want to be able to say, if I put a controller on this robot, it is not going to run into an object. All right. This might sound like a fairly obvious statement, but down to like a very primitive level, it is hard to provide that guarantee, even on something that is very idealized right now. So there's theory and experiment to be developed there. And then that's some work that I'm working on with my colleague Sriram. And finally, environmental robotics, an area that I think is just one of many applications in which, even if all of these very large bets that industry is making in autonomous vehicles and robotics today, whether it be sidewalk delivery robots or autonomous driving or any kind of autonomous flight capabilities, there are going to be a lot of applications that are totally off, not solved by those solutions. So even if there is an autonomous vehicle driving around, making millions of miles in the middle of cities, whether it's snowing, raining, I don't think it's going to solve problems in field robotics like this. And the reason why I say this is because the terrain issues here are just absolutely different than what you have to worry about when you're driving on a sidewalk. And I don't think that there's a very strong profit motive to solve these problems. Like, we need to be the ones that are solving the like getting technology built out to help our planet. So this is one area that I'm really passionate about. I do want to discuss 2 last things. One of them is that we have a textbook. By we, I mean me and my colleagues here in robotics. So Brad, Alessandro, Nicholas, and I have this textbook that's being published by MIT Press. I think this is a nice extension of the work that we were previously able to do in our classes. And I think that this is going to go to solving problems like this one, being able to build and develop more engineers and scientists that can solve these problems themselves. Hopefully, I see this as a really important aspect of the work that's being done by roboticists today, is educating more roboticists. And the last thing is that I'm very proud to say that I've graduated a few students that were that have gone on and actually taken this mantle, been scientists and engineers, and continue to do that work today. And so this is just a list of here are the PhD students who have graduated from my group, and one postdoc who's gone on to be an assistant professor, also doing field robotics, and was a great collaborator with us during Marble. I'm super proud of all the work that they're doing today and all the work that I was able to present today as a result of their hard efforts. And here's the current team. And of course, all the problems that I said are future work, they're being solved today by this group of students. We have an ICRA deadline tonight, and many of them are wondering if I'm ever going to review the manuscripts. Don't worry, I will. And so with that, I'm going to take your questions. Thank you. Yes, Claire.
Why did you bother with the radar?
Why did I bother with the radar?
Yeah.
Yeah.
LiDAR too expensive.
Oh yeah, so the visually degraded environment thing is super important. So LiDAR and vision work in very so similar frequency domains that you can actually plot the intensity returns on a LiDAR image, and they look like a grayscale RGB image in the visual spectrum. So in fact, we were thinking about using that as an artifact detection technique before we realized that they have red backpacks, not gray backpacks. That's a very nice, strong indicator as an artifact. So that's one big deal, is that the problems that are going to be solved by LiDAR and vision are completely, they will be in a different class of challenges than with radar. The second thing is that, yeah, those automotive LiDARs that I showed, they are heavy and they're big, and they cannot easily sit on a UAV. Although you did see a few teams, in fact, every team that flew a UAV did put an automotive grade LiDAR on their UAV, their quadrotors. The way that they got by with that is they had 10-minute deployment times. So they all launched from the back of other vehicles. I think that there are pros and cons, and there's a big design space to be considered here, but I think that radar gives us a lot of opportunity that will never be achieved by those other modalities.
So just to follow on, the ML, was that essentially learning a virtual sensor, like a synthetic LiDAR, where you could basically,
Yeah.
you map between where you have dense LiDAR and sparse radar.
Precisely.
Then, okay.
Yeah.
Actually, so NOAA is super interested in that sort of thing for synthetic radar.
Yeah.
Because we don't have radar everywhere.
Yeah. Yeah, those kinds of transfer learning, like there's some style transfer that could be considered for that, for instance, but for our application, is actually far more mundane. And it did have some significant limitations. One of the biggest ones being that, as I mentioned previously, radar can see through objects, LiDAR cannot. So if you use a positive supervisory signal from LiDAR, your radar is actually dropping a bunch of signal that you could otherwise get. Coming up with self-supervised techniques for radar is still beyond what we've done, but it's definitely something that we're very interested in. And it's that data set that we collected that's totally one of a kind that I'm very proud of. Yeah, that's going to be the unlocking mechanism for that, I think. Dan.
First of all, great talk. I learned a ton about robots and back at work, but one question that I had was whether or not the robots that you are deploying that are working as a team are ever like directly communicating with each other. Everything that I learned about today was sort of individual robots. So
Yeah.
Can you say a little more about that?
Absolutely. Yeah, I skipped the entire communication section. Harel is like, wants to jump up and talk about the communication solution because it was really, really cool. So there were a couple of new innovations that we came up with for that. Yes, the robots were talking with one another, and it actually required a fairly significant re-engineering of the entire layer 2 protocol for how you reconnect on Wi-Fi. I mean, that sounds like insanity, but it's what happened. The reason was because when a robot comes into communication, it might only be for a split second. A lot of Wi-Fi connectivity, like reassociation techniques today, may take seconds to be able to do that. So we're constantly doing something that is akin to sending a broadcast storm through layer 2 in order to do the fast reconnections. And what is being communicated are the maps and eventually just the pose graphs from those robots. So it's like, where have you been and what did you see? And if you saw any artifacts, tell me about those too. So that if I ever go back home, then I'm going to be able to tell the human supervisor about the artifacts that you saw. And I'm going to be able to deconflict paths between what you've done before and what I should do. And if you see any walls or anything like that, I'll probably get an idea of that based on this sparse map that you shared with me. And that's largely the solution that we came up with. It was actually, I mean, it was one of our most tested components of the team. I'm sorry that I couldn't talk about it, but I would be really happy to talk about it more. But yeah, there was a lot of robot-to-robot cooperation that occurred during that competition. Yeah, it's so much work. I mean, a lot of people's work. Yeah, I saw your hand up next.
Two raised hands on Zoom.
Sure.
Danny and then Carla, do you want to ask your questions?
Sure, yeah. So we are so proud of you, Chris, you and the team, and Eric Frew, and everyone, the students and everyone else. So you made us proud, and I wanna, if I was there, I would give you like a big hug or a fist bump or whatever you feel comfortable with. So the question that I have, so while it's fascinating, the robots, I think one aspect that I want everyone to be aware of, it's how fascinating was the human aspect, right? When you said that the team was so diverse, it had so many students and so many departments, and that you called it the managers, and I'm sure you've done a retrospective after the whole big success to look back and analyze what went well and what can we do better. And since this is such a diverse team and such a unique team that you've put together, what's one key lesson that you can share with us from the point of view of building and running and managing and leading teams that went well, and you say, this is worthwhile emulating, and we are going to do the same. It's a best practice that we want to repeat in the future. And maybe if you're comfortable sharing, what's one lesson that you learned that, if we ever do such a diverse team, a large diverse team in the future, maybe we should do it differently than we've done.
Yeah, thank you, Danny. And the one thing that I wanted to say is that, it took me a lot. I searched my soul a lot to think about what I was going to talk about today. And I ended up talking a great deal of time on Subterranean Challenge at the expense of other projects that we're doing and excited about, because I feel like there's so many more lessons to learn from Subterranean Challenge that might be more applicable to non-roboticists and to roboticists than other topics. And so I just want to acknowledge that while this was quite a retrospective, I think that, I tried to convey some of the wisdom that we picked up. The one thing that I will highlight from that list, in my opinion, was most important was the ability for a team to like get back off its feet after a failure, and also what a pivot looks like, what a good pivot looks like. So I think that there was a bad pivot that happened after Tunnel. We decided to add more platforms. We decided to, we felt really good. We got 4th place among all teams, which was actually really, really good. Okay. And like, in our opinion, we were riding high and we were like, how do we beat the next 3 teams? So what we decided to do was take on more. And that was a total misstep, like absolute steering the ship right into the black hole. And I think that what we should have done was say, like, we need to freeze the things that did well and then add a few extra things. So that's just one piece of information I would say is like, you know, it's easy to feel like, oh, wow, we got a success. Let's chase more success in a very aggressive way. And what ended up happening was like, you know, some people quit the team after Urban, you know, like, and it was sad. But I think that that's like something that we should, I would say, is like a, you know, a lesson to be learned. I guess that was probably more answering your second point. To your first point, I mean, I think that I talked a little bit about those, you know, buy versus build, and what is a good team? How do you include management in decisions? And I was talking a lot, you know, with our team members about like, you know, what is it that you would like to see from this team? And in fact, I don't want to take even credit for that project engineer idea. We asked the students, you all remember this, we asked the students, what do you think we should do after Urban? And they conclaved, and then 2 of them came up to us and said, we think that we need to lead the project. Yeah, no kidding, right? So I mean, I think that's you know, we were looking for any success anywhere we could get it, and we went to our students. Whoa. Yeah, I mean, like they were the ones who came up with these ideas. And so yeah, those are just some thoughts. Hopefully they're helpful.
Let's take one more question
Absolutely.
and then let everybody else leave.
Yeah. Would Carla mind waiting? Because there's one more question in the room. I think I saw one hand. Yeah.
So I see that you're writing publishing papers on radar. How do you make sure the other teams will use your research?
The competition's over, yay! So it doesn't matter if they do it. And yeah, that's part of the point. You know, there's a natural publication delay because people having to review things, and by the time you see what I'm doing, unless I give you the code for it, then probably not that useful. And honestly, it was quite collegial at these competitions. I mean, we would go up to people and be like, yeah, our USB cameras keep failing. They're like, the same thing happened to us, and this is how we solved it. Here are things that we tried. We had engineers from other teams looking at our systems and vice versa. And you know, like the first thing that happened when CSIRO had that robot come down, crashing down, they laughed and said, "Everyone, come look at this." I mean, so it was actually like, you know, there were no advantages to be gotten through, you know, this kind of unscrupulous behavior. I think that a lot of people wanted to be, you know, as open as possible. Great question. Cool.
All right, let's thank our speaker.
So that I can go to the next question from, yeah, is she still on?
Yes, I'm here. Can you hear me?
Yeah, okay, great. Can I get you, what was your question?
So my question was just that you mentioned the dense radar images, and I was wondering, is it better for the robot's perspective, for him walking or for the moving, to be denser the images or not?
Yes.
So
Yes, yeah, absolutely. So dense radar images is a data